This is the hardest math question I got asked at the National Olympiad, ever. It is an elementary maths question. The statement is so simple that it barely spans one line. But a solution does require a lot of creativity that literally no one in the exam had. This problem was set at the Romanian National Olympiad in 2015 for students aged 13 to 14. The highest mark anyone in the contest got for it was 4 marks out of 7. Barely halfway. I got a remarkable 1 mark out of 7 this year, despite spending a lot of time on this question, literally trying anything from basic number theory theorems to Fermat's last theorem. So before we jump right into the statement of this question, I just want to give you a very warm welcome or welcome back to my channel if you're a regular. My name is Ioana and I am a 4th year math student at the University of Oxford. Many of you ask me to solve actual math questions and do actual maths on this channel from time to time, and my first thought when I read such comments was to do this question. It was literally the first one that came to mind. So let's see what the fuss is all about. So we have this very cute looking statement. We want to find all non-negative integer numbers n for which n plus 8, 2n plus 1 and 4n plus 1 are simultaneously perfect cubes. So the third power of an integer. That's it, literally as simple as that. How do we approach such problems? Well, obviously the first natural thing to do is to just start small, see how these numbers look like for various small values of n, and hope for some sort of pattern to be observed. So for example, let's say in the first step we want to look at, let's say n equals 0, because this is the smallest number that we can take. And for n equals 0, we have the numbers 8, which is 2 to the 3, so we're lucky for now. 1, which is 1 cubed, and then 1 again, which is 1 cubed. So n equals 0 is actually a solution. We're happy. Now if we move on, we see that for n equals 1, we have that n plus 8 is actually 9, which we don't like, it's not a perfect cube. N equals 2, we have that n plus 8 is 10, not a perfect cube again. N equals 3, we see that we have n plus 8 equals 11. And we can see that actually these numbers increase by 1 every time. So let's say until we get to n plus 8 equals 26. This is for n equals 18. This is again not a solution. And we notice that we won't find any perfect cubes in this interval because there are no powers of 3 in between 11 and 26. The next power of 3 is gonna be 27, which is 3 to the 3, which occurs for n equals 19. So for n equals 19, we actually have, which is a perfect cube. But then we notice that we look at 2n plus 1, which is 2 times 19 plus 1, which is 39, which is not a perfect cube. So we're kind of stuck once again with this question, even if we tried 19 cases that did not lead to a solution and 1 case that actually led to a solution. So now what? It seems like we might be able to find something further down the line of natural numbers, but we need to find all solutions nonetheless. So trying more numbers might just not be the way forward here. We tried quite a few numbers here. We saw that a clear pattern has not really been formed, so it's time to try something else. And by the way, very few people got anywhere beyond this point in a competition, so even if you only spotted these particular cases, you should feel very happy. So let's see if we can deduce anything more general here. So what do we know from the problem statement? We know that these 3 numbers all need to be simultaneously perfect cubes. So let's express this mathematically. So let's say that n plus 8 is something like a to the 3, where a is some integer number. We don't really care who it is for now. Then we have that 2n plus 1 must be some b to the 3, and then 4n plus 1 must be some c to the 3rd, and again b is in z, and c is in z. Now, here comes actually the key idea. We know that these 3 numbers are all perfect cubes. So who else can we say, just by looking at these, that is also a perfect cube? What else can we deduce? We can deduce that another number from this will be a perfect cube. What number is it? Well, here we need to take advantage of what we know about exponents, right? So we know that ABC, all to the 3, is a to the 3rd, b to the 3rd, c to the 3rd. So this is also a perfect cube. But in our case, this is actually something more interesting. We know that ABC, all to the 3, is just gonna be n plus 8 times 2n plus 1 times 4n plus 1. And this is actually a perfect cube. And this is the key to solving this question that literally no one thought of in the Olympiad. Because like just taking this product seems quite natural when you see it, but just coming up with it, especially when you're at such a young age, you don't really feel like this is what you should do. And even after this point, it's not really clear what you should do further down the line. Now, what do? Well, we have some parentheses here. We know that this is the product of three numbers, so there are just three numbers multiplied. So we can just expand the parentheses and see what we get up to. So hopefully I don't mess up the algebra. So after expanding the parentheses and hoping that we did not make any algebraic errors, we notice that we have that this whole number here must be a perfect cube. So what we really like about this polynomial that we have here is these two factors actually. What can you say about this? Well, both of these are actually perfect cubes, aren't they? 8n to the 3 is just 2n all cubed, and then 8 is just 2 cubed. So we have the sum of two perfect cubes plus two extra factors in here, which gives us an idea that maybe, we don't know for sure, it might be helpful to compare this number, right? So compare this here to just 2n plus 2 all cubed. Because we know that from the binomial expansion, or at least we hopefully know from Pascal's triangle, that this is looking somewhere close to this number. So let's just expand this here and see if we can maybe find an equality if we're lucky, and if we're not lucky, find some sort of inequality between these numbers to see where this perfect cube must be standing. Alright, so now we need to expand this number. I put the formula for the binomial expansion of a plus b cubed right here so that it can help us and we can reference it to expand this number. So we know that this is just 8n to the cube. And now we compare this. What do we know? We know that our number from before, which was 8n cubed plus 70n squared plus 49n and plus 8 is a perfect cube. But here comes the thing. These numbers, these two numbers here, the number that we know is a perfect cube, whatever n is, and the number that we know must be a perfect cube for some values of n that we need to determine are not actually the same. But obviously, just by looking at our number here, we notice that our 8n to the third is the same as this, and our 8 is the same. But also we can definitely establish something in between the other terms, right? Like, just by looking at them, we know that 70 is bigger than 24, and 49 is bigger than 24 again. So this clearly just shows that 40n squared is gonna be bigger, strictly bigger than 24n squared, provided n is different than 0. Because n equals 0 is the only one that doesn't preserve the strict inequality here. And then 49n is gonna be bigger than 24n, again, provided n is different than 0. But we can definitely just assume that n is different than 0 because we've already established that n equals 0 is a solution. So this actually brings us to a very nice conclusion here, which is that our number 8n cubed plus 70n squared plus 49n plus 8 is always gonna be bigger than 2n plus 2 cubed for all n different than 0, which is something that will be very, very helpful further down the line. Now, how can we use this lower bound, this inequality, to determine all values of n so that our left-hand side is actually a perfect cube? Here it might actually be very, very helpful for us if we can find an upper bound for this number, and moreover an upper bound which is a perfect cube, just like our lower bound. You might be familiar with the technique of squeezing a number between two perfect squares or perfect cubes in order to determine that a number cannot be a perfect square or perfect cube respectively. So let me show you what I mean by this. So let's take the number 10. The number 10 is definitely not a perfect cube. We can tell just by looking at it. We know that there's no a such that a to the 3 is 10, where a is an integer. But what if this number was bigger? How can we establish this sort of conclusions from this? So a very helpful thing that we can do is know that 10 is bigger than 8 and smaller than 27. And 8 is 2 to the 3, and 27 is 3 to the 3. So logically, there is no value of a in z for which a to the 3 is equal to 10, because a would have to be bigger than 2 and smaller than 3, which is obviously nonsense. So this is something that we want to adapt in our case. It would be very helpful, it would actually be very much ideal if we can prove that our number here, so 8n to the 3 plus 70n squared plus 49n plus 8, which we know is bigger than 2n plus 2 to the 3, would be smaller than 2n plus 3 all cubed, In this case, we would know that there are no n's such that this is a perfect cube, and we can say that this problem is finally solved. So is there any way in which we can establish this inequality? The only thing that we can do really is to try it out and see what this number looks like. Can we tell if this number is bigger than this? Well, not really, because our coefficient of n squared is not bigger than our coefficient of n squared here. So this is not really a true thing, this is false. But does this mean that our whole idea is broken? Well, not really. We have just gone one perfect cube up from our lower bound, and we have established that this is not an upper bound. Well, everything is definitely not lost, because if we don't have an inequality here, but can we actually have an equality? Can we find a solution from this? We might be lucky. So let's see what the equality case would imply here. Well, just by simple arithmetic, we have that if these are equal, we would have that 5n plus 27 minus 8, so 19, equals 70 minus 34, which is 36, which is 34n squared. Obviously, we can equivalently write this as just n times 34, n minus 5 equals 19, which we know how to solve very easily. Well, n is an integer, and we know that 19 is prime, so we either have that n is 1 or n is 19. If n is 1, we would have that 34 n minus 5 is equal to just 34 minus 5, which is 29. And 1 times 29 is 29, which is not 19, so this is false. And if this is 19, then 34 n minus 5 is gonna be a lot bigger than 1, which would be 19 times 1 equals 19. So obviously this case does not lead to any solutions, so we cannot have this equality right here that we have established. So what do we do now? Well, just because our upper bound here, that was just one perfect cube above our lower bound, did not work, it doesn't mean that we cannot go further up and maybe find an accurate upper bound. It's actually quite similar to what we did before from now on. So we know that this number, for which we must find all values of n such that it is a perfect cube, is bigger than this perfect cube here. And then we just want to go up. So can our number be equal to 2n plus 3 all cubed? No, we have established this before, just here. Then we want to move up. Can this be equal to 2n plus 4, 2n plus 5, 2n plus 6, whatever, all cubed? And then maybe further down the line, we either find solutions or we can establish a strict inequality, and then we basically catch this number between consecutive with a few values in between that we proved do not work, perfect cubes. And in that case, no further values of n are possible, and we can just take our conclusion from this. But let's take them one step at a time. So let's see if we can have an equality with 2n plus 4 all cubed. So, is the perfect cube here that we have 2n plus 4 all cubed bigger than our number? Well, we again cannot really tell due to the fact that here the coefficient of n squared is 48 and the coefficient here is bigger. So again, we cannot establish this. So we need to both look for a solution here. So we need to solve the equality case, and we need to move further down the line to 2n plus 5 all cubed to hope for an inequality finally. But first, let's equate these and see whether we can find a solution. So just by equating this, we get a 22n squared minus 47n minus 56 must be equal to 0, which means that n times 22 n minus 47 must be 56, which again we solve using the same method as above, and I'm not going to bore you and go into the details. It's just very, very simple. N can be any of the factors of any of the divisors of 56, and we note that after trying all of these cases, this again leads to no solution. So we need to move up. We need to move to 2n plus 5 all cubed, which we proceed just as above. We find the expansion, which is... So can we tell if this is bigger than our number? Well, not really again, because this coefficient 60 is not bigger than 70, but we're getting very, very close. If you can see, before we had a 48, here we have a 60. So maybe when we need to go further down the line, because we know we need to now, maybe this will actually be a suitable upper bound, and we will know that we're done. We cannot find any other n. But before we get there, let's not get ahead of ourselves and establish the equality case, see if we can find anything from here. So if these numbers are equal, then the equation that we need to solve is simply 10n squared minus 101n minus 117 equals 0, or equivalently n times 10n minus 101 equals 117. 117 we know is 3 times 29. So again here we need to take the cases where n will be 1, 3, 29 and 117. And again, I'm not gonna bore you with these 4 cases. You can just take them very, very quickly and see that there is no solution in this case either. So now let's go to 2n plus 6 all cubed and hope that this will actually be a suitable upper bound. So we can take again 2n plus 6. So let's see if this is actually an upper bound. Well, now we see that very, very nicely all of our numbers are actually bigger than the ones we have downstairs. So 72n squared is strictly bigger than 70n squared, provided again n is different than 0. 216n squared is bigger than 49n, 216n, sorry, and then 216 is bigger than 8. Again, this is provided this. And so we can just add all of this to see that 8n cubed plus 42n squared plus 216n plus 216, which is 2n plus 6 all cubed, is bigger than my number 8n cubed plus 70n squared plus 49n plus 8. So we know that we've got the following very, very beautiful chain of inequalities, which is that 2n plus 2 is less than, this is again provided n is different than 0 here, less than 8n cubed plus 70n squared plus 49n plus 8, less than 2n plus 6 all cubed. And we know that anything in between, so 2n plus 3 cubed, 2n plus 4 cubed, and 2n plus 5 cubed don't work. So these just don't work. So clearly we see from this that we do not have any other solutions for n integer. So we don't have any solution n in z and different than 0. So our answer to this problem is that n equals 0. And this is our one and only solution that we find. So yeah, this was the question. It took us quite a while to go through everything, to explain everything. Let me know if you have any questions. I really hope that I've done a good job of explaining this. It is my first time explaining math on this channel, so forgive me if I did not do a great job explaining this. Well, as you can see, it's definitely not the most beautiful problem. I definitely do not really like questions that have a lot of algebra, that have a lot of computations, that are very, very easy to get wrong, especially in exam setting under pressure. But again, this is Olympiad, so maybe the expectations are higher as well. I normally prefer questions that require more creativity than to go for heavy algebra, but it is what it is. I really hope that you guys have enjoyed this. Please let me know in the comments what you think about me doing maths on this channel as well. Let me know if you have any maths problems or maybe maths contests or exams that you would want me to try on this channel if so. And yeah, definitely give this video a like if you enjoyed it. Comment down below any video suggestions, again, any questions that you might have. And don't forget to subscribe if you want to see more of me, more university content, more maths content, and more studying tips and advice. And if you want to see more of me, definitely go on my Instagram, give me a follow there. I'm definitely a lot more active. Definitely enjoy the rest of your day. Good luck in your studies. And I really hope to see you in the next one. So goodbye.
I'm sick of daydreaming. I just want the feeling of you in my bed. I'm down to just waste time right below your waistline. Want you by my head.